So good day everyone, this is our report chapter 11 inferential statistics. So when we say inferential statistics, it only pertains to the test or the method that researchers used in order to draw a conclusion in the population sample data. And it actually assesses whether that data is reliable or is just due to chance. An inferential statistics came from a general linear model which includes t-tests, analysis of variance or ANOVA, and analysis of covariance or ANCOVA. Standard deviation unit or z-scores. Z-scores or standard deviation units allow researchers to determine a score's position within a normally distributed set by using the mean and the standard deviation. When we say the mean, it only pertains the average of the overall scores. And when we say the standard deviation, it means how much does each variable varies from one another. They measure how far score deviates from the mean and the score into the z-scores to express its distance in standard deviation. So in other words, we will convert the answer into a standard deviation or the z-score. The formula is z is equals to x divided by a, where the x is equals to x minus x, which means the score minus the mean of the distribution. In the standard deviation here in the example, it was given, assume that the example is 80%, that 80% of an examination where the class average is 75. So in the example, we will assume that at least 75% or 75 was the average, and the standard deviation was 5. That is because that the z-scores would equals to the score, which is the 80, and the average, which is the 75. That's why we get the answer of 5. And then we divide that, by 5 again, so we get that answer of 1.0z. Based on the z-table, area between the z and 1, which is 1.0, or 3.413, or roughly 34% of the area above the mean. Now, because that 50% is below the mean, which is here in our example, because the average is actually 75%, the score would be approximately 50 plus 34, which we will get the 84%. Which means that only 16% performed better on the test. And similarly, a score of 75 yields the scores of 0.0, because 75 again is our mean or the average, which beats the 50% of the score below the mean. Hence, z is equals to 87 minus 75, which means that, which will equate to 12. Then we will divide that by 5, which is our mean later on, which will equates to 2.4. And it is covered by the 49.18% percentile of the positive and 50% of the negative, or 99.18%, which is here in this sample. In addition to being useful in calculating percentile, area z-scores are also important in assessing probability levels. So z-scores is also useful in assessing the probability of a certain variables. Now next we will go on to the chi-square or x-test scores. The chi-square symbolizes the Greek letter chi squared or x squared. It's a test of the independence of the relationship between nominal and categorical variables. It asks whether the two variables are independent and exhibit no relationship or association due to chance, or dependent when the relationship is real and would seldom occur during the chance alone. So here in chi-square test, it is actually used by researchers in order to assess whether the two variables are independent or have no relationship at all, or whether they have a relationship but it is only due to chance. Chi-square test, basically the chi-square statistics compares the observed cell frequencies with the expected cell frequencies, or values that could be expected by chance. So when we say the observed cell frequencies, this is the cell that we actually know. And when we say the expected frequencies, this is the expected results that the researchers are actually expected. The formula is x squared, and these letters, the symbol of m, and then O of f minus E of f 2 divided by E of f, where the O of f is the observed frequency, E of f is the expected frequency, and this symbol is actually sum of all each cell value. Utilizing the data in table 11, the following process will result to the function presented in table 12. For example, from the top left cell here in the expected frequency, 200 is equals to 25, because 50 times 100 divided by 200 is equals to 25. Then the expected which is our expected frequency. Now the expected frequency in the bottom right cell will be the 150 here in table 12 times 100 divided by 200, which will equates to 75. Now, applying from that, we get the expected frequency, and here it is also given in the example in the table. In the chi squared x squared test, now we can now apply the formula, which is the 40 minus 25 divided by 25 squared divided by 25 plus 10 minus 25 squared divided by 25 plus 60 minus 75 squared minus 75 plus 90 minus 75 squared divided by 5, which will equate to 225 divided by 25. And this 225 plus 225 divided by 25 plus 225 divided by 75 will now, if all in all, the equation will result to 24. Now we can calculate the appropriate freedom. The appropriate freedom is the formula here is that d of f, or the difference in frequency, is equals to r, which is the rows, minus 1 times the columns minus 1, which is letter C. The degree of freedom refers to the number of cells that are free to vary. So when we say degree of freedom, this is actually the number of cells here in the table 12 that we used. These are the number of cells that are free to vary. When we say free to vary, it only means that it is free to be compared from other cells. That is once that the value of the certain cells are fixed, the others are no longer free to vary. So once the other cells are fixed, the other cells, it cannot be varied from the other cells. So let's say that here in the example, let's say the cell is set at 20, the other cell values are determined by the subtracting from the marginal. So our marginal here is 20, and the other cells will be deducted or subtracted from the 20. In the example above, the degrees freedom from 3 by 2 table, d of f is equals to 2. And for example, for 3 by 3 table is 2 minus 1 and times 2 minus 1. So how in the world did it become 2? It became 2 because we have at least 2 tables here in the table 12. That's why 2 minus 1. We just both for the rows and the columns. Now we just substitute that 2 here in the formula. 2 minus 1 times 2 minus 1. So, hence, we get the answer of 1. Chi-squares had this example been reflected in the research work, researchers would have presented that is x squared is equals to 24, and the difference in frequency is equals to 1. So p, the probability value, which is less than 0.01, or a chi-squared of 24 with 1 degree of freedom, it is statistically significant, and at 0.01 level of probability, only 1 in 100 times could such result could have been obtained solely because of the sampling error. So the results would be like in every 100 samples, there at least this kind of results here in table 12 will appear at least once, and it might be only due to error. Had the calculated value not exceed expected value, it would have been described as not significant at the 0.05 level. This is the chi-squared test of significance. So if the value was not been described, then it will not be significant at the 0.05 level. Chi-squared accommodate any number of cells. Although the large number of cells, the likelihood increases and that there may be few values. In some cells, this is a situation that distorts the chi-square statistics. So in chi-squares, it also accommodates the number of cells. Although with a large number of cells, there's a likelihood increases that that maybe a few values in some cells where it will commit some errors. But in statistics, in such cases, it is actually recommended that number of cells be collapsed or combined. So here in chi-squared value, it is actually being recommended that that all of the cells, their values will be combined. Chi-squared is also unstable in the 2x2 case, and especially if any of the expected cell frequencies are less than 10. So if any of the difference frequencies is actually less than 10, then it is actually unstable. Such circumstances, one should employ the Yates correlation, in which 0.5 is deducted from the observed minus expected frequencies in each cells. Similarly, if any of the expected cell frequencies are less than 5, then the researchers should apply the Fisher exact test. So if there is at least correlation of at least 0.5, then it is actually deducted from the observed values. And if it is like at least exactly around 2, then it is actually being added. The difference of mean analysis, the t-test or student's t-test, is often used in criminology to compare the means of two independent groups. So here, in the next part, we have the t-test. In t-test, we actually compare the means or the average between two independent groups or two separate groups. Many mistakenly believe it was named for its benefit to the students, but the name actually comes from the pen name of William S. Cossett. So this t-test is actually came from William S. Cossett, and it's not actually from some students who developed the test while working at a brewery. So William S. Cossett developed this test while he was working in a brewery or in refining of wine. Cossett faced challenges in adjusting brewing formulas based on varying grain quality, leading him to create statistical method to predict the optimal mixtures. So because of that problem, William S. Cossett developed this t-test score. The inquiry resulted in a t-test which helps researchers determine the means of two groups are significantly different. A significant t-test allows rejection of the null hypothesis. Thus, assumption of no difference with no non-significant result suggests that any observed differences could be due to random sampling error. So here in t-test, it actually rejects the null hypothesis, and any random sampling error and any differences is actually only due to random sampling error.
Difference of mean analysis or t-test. Some type of random or probability sampling is assumed. Number 3. The variables being sampled come from populations that is normally distributed. A full explanation of t-test requires at least full chapter in the standard statistics textbook, and it's not possible in this portion. Only the three most common types of computations using the t-test discussed here are the following. Number 4. The t-test for large sample or n equals 30 for both sample in case t-test is the same as z-score standard deviation. Difference of mean analysis or t-test. The t-test for large sample or n equals 30 are both sample. In this case, one test is the same z-score standard deviation. Difference of mean analysis or t-test. The t-test for small samples, if either group is less than 30, an adjustment formula is required. Difference of mean analysis or t-test. The t-test for correlated samples are pre-test and post-test as the same group before and after. The t-test for larger sample are calculated using the sample from the first illustration and the first formula. Difference of mean analysis or t-test for sample containing 30 or more calculation of t-test is the same as that of z-scores. This is the alternative formula that must be used for t-test if sample size are below 30 or are of unequal size, or if match samples before after are being compared. Difference of mean analysis or t-test. The primary purpose of this discussion is providing the reader with a general ability to interpret and understand research using such tests, interpretations of z-scores and tests of significance is dependent on a full understanding of figures such as the following. Difference of mean analysis or t-test. In sample calculation, 12.39 is the significant in two-tailed at the 0.05 level and which requires a value of at least 1.96. Thus, a difference in sample means of between 10 and 12 is sufficiently large to permit researchers to assume that difference exists in the population from which of the sample were drawn. Analysis of variance of or F ratio test. When researchers need to compare 3 or more groups, using multiple t-tests becomes impractical and increases the likelihood of finding significant result by a chance. Instead, analysis of variance ANOVA is employed to compare 3 or more sample means efficiently. One-way ANOVA is used when examining a single independent variable with multiple categories, such as comparing different income groups on a fair of crime scale. There's also two-way ANOVA, which analyzes two independent variables simultaneously. Analysis of variance or ratio test. The fundamental principle of ANOVA is that the variation between groups should be greater than the variation within groups. For instance, if comparing the professionalism of officers from 3 government agencies, a high professionalism agency should show more professional scores compared to medium or low professionalism agencies, indicating significant difference among the groups. Analysis of variance of ratio test. In Table 13, a sample of 5 officers from the 3 government agencies suggests that although lower professionalism government agencies have some officers with higher professionalism, the rulings that some higher professionalism government agencies in general, it appears that the characterization are useful types. Analysis of variance or F ratio test. ANOVA goes beyond such as judgmental approach and examine this question statistically because the researcher is asking whether the difference that do exist are due to chance or sampling error. Table 13 presents the professionalism in government service. Analysis of variance or F ratio test. The basic idea of ANOVA is to have the large variance between groups and small variance within groups. ANOVA use the F statistic which is similar to t-test and z-scores. As a table of probabilities with which the calculated statistic is compared, ANOVA is a very complex process and summarized below. Simply to acquaint the reader with how the F statistics is obtained, it is not expected from this brief presentation that researchers to able to perform ANOVA. ANOVA can be viewed as a series of steps lead to completions of the Herander chart. Table 14, the chart depicting completion of ANOVA. Analysis of variance of ratio test. Table 14. Analysis of variance of ratio test. Calculate the sum of squares for the SS total. This given is the example. Calculated the squares between groups or students. This also example. I thank you.
Table 14 chart depicting completion of ANOVA. So, first, calculate the sum of squares for the SS total. This is given in the example SS1 is equals 121.33. Number 2, calculate the sum of squares between groups of the SS interval. This is also in the example. Number 3, calculate the sum. So, dyan may mga calculation which is ang steps ngayon is pag-perform it analysis to variance or which is tinatawag na ANOVA. ANOVA. So, ANOVA or F ratio test. So, saya nga statistical test is ginagamit para ma-compare ang multiple groups para ma-determine if may nga significant difference between sa anda. So number 1, ija is calculate in total sum of squares or gatawag nga SS total. So, ayang nga measure is overall variation if isa ka data. So, sa number 2, calculate the sum of squares between groups or SS between. So, ayaman hay ang measures nga variation it ng means para sa different groups. Next is number 3. Calculate the sum of squares for within the groups, which means ginakalculate na ang sum squares within sa groups lang. So, aya is measure cut imo nga gitawag nga SS within. So, aya hay do measures nga variation with each group. So, ay pag total hay SS within is equals to SS total minus SS between. So, ito may anaran din nga pagka-solving. So, next is ginakalculate ang degrees of freedom where is k number of groups and categories being compared. Number 5, dito ay ginakalculate na ang variance between groups kung ginaan is S square root of 2b and within group of S2W. Next is the analysis of covariance or ANCOVA. So, analysis of covariance or ANCOVA is a general linear model with one continuous outcome variable or quantitative and one or more factor variables or qualitative. ANCOVA is a merger of ANOVA and regression for continuous variables. ANCOVA tests whether certain factors have an effect on the outcome variable after removing the variance for which qualitative predictors or covariates then account for the variability. The inclusion of covariance can increase statistical power because it accounts of some already. So, ANCOVA, which is statistical tool na mag-help sa atin para ma-understand natin may do different between different groups or factors nga ma-affect sa atong continuous outcome. So, while gina-considered man yung influence sa factor na ma-measure natin o ginatawag natin nga called covariance. So, imagine, nag-study ang kitang effect or different teaching methods. So, on student test scores, kailangan mo i-compare ang average scores sa isa ka grupo. Pero, what if some students high natural better at a subject than others? So, ANCOVA is nag-allow mo it-account for the difference or covariates para mabuo nimo ang accurate picture kung paano ang teaching methods para kumbaga paano na ma-impact ang mabuo nimo nga score. So, sa simple term, ANCOVA hay gabulig sa ato para ma-isolate ang specific impact of one or more factors sa magiging outcome while naga-controlling imaw for the effects of other factors nga pwede na ito ma-influensyahan ang magiging resulta. So, sa analysis of covariance or ANCOVA, so example guys, research are interested in comparing the IQ scores of movie of males and females. However, they want to consider the impact of another variables of this score. So, in this covariate is not explicitly mentioned in the provided text, but is likely a variable that is related to both IQ and gender, such as age, education level. So, daya by using ANCOVA, ang researcher hay makakontrol it effect para sa covariate. So, nag-allow imaw para mag-obra it more accurate and comparison sa IQ score between males and females. So, Sa summary, statistical table 16 provided. At nandiyan sa next page. Sa table 16, sa example, sa summary. So, ang information ngayon ay sample size, IQ scores, male and female. So, hayan data is ginagamit na ma-perform. So, is ginagamit natin dyan is ang ANCOVA analysis para ma-determine natin if may significant difference ang IQ sa dewa ka ang groups, which is ang male ag female, even after counting of the effects of each covariate.